This is a clock stage prop I made. It can tell the time, but the hands can also be programmed to jump to a scripted cue, to run fast, pause, move backwards, or show impossible times on command. And you can control them via a DMX signal sent from a lighting desk or programmed into your show control software. So here I've made a simple control panel in QLC+, and then I can manually move each hand to a specified angle using this controller here, or I can get them to indicate a specified time. Now, I've done playful projects with clocks before, sometimes modifying a regular clock mechanism as you'll find in a wall clock, or else using a dual shaft motor designed to move indicator dials on a vehicle dashboard. But for this project I needed something bigger and more impactful and with enough torque to move these large clock hands. So I wanted something more like the NEMA 17 12-volt stepper motors that you find in 3D printers and CNC machines. The problem is that generally those motors only have a single shaft. Now, because all the hands on a clock rotate about the same fixed pivot point, if you want them to move independently, you've traditionally had to use one motor per hand and a series of cogs or pulleys to turn concentric shafts to which the handles are attached, like this. But I recently discovered that there is a manufacturer that makes concentric dual shaft stepper motors, and that means you can attach them directly onto the hands with no more components, and that's exactly what I'm using here. So this is essentially two stepper motors stacked on top of each other, and they can be controlled completely independently from each other, rotated in different directions and at different speeds. Now, I'm using an Arduino with a stepper motor driver shield to control them, and I've also added an RS485 transceiver to expose the device as a DMX fixture. So I can have the clock on the same network and controlled by the same controller as my lights, my fog machine and other stage effects. Now, the ramp shield I'm using is just for convenience. They're cheap and readily available. It provides stepper driver sockets, motor connectors and enable pins, and it just stacks on top of an Arduino Mega. A standard ramps board actually has capability for 5 stepper motor outputs, but this project only uses 2 of them. I'm using the X-axis output for the hour hand and the Y-axis output for the minute hand. You could use any other stepper shield if you prefer. And then the Arduino receives a DMX signal through an RS485 transceiver module, which is wired into the GPIO pins attached to the Serial 1 interface. And here's a wiring diagram to show those connections to the motor more clearly. So this is a bipolar stepper motor. It's got 2 shafts, each shaft has 2 coils, and each coil needs 2 wired connections, one at either end. So that's a total of 8 connections wired between the Arduino shield and the motor, 4 for the hour hand and 4 for the minute hand. Now also note the order of the wires as shown here. There's no standardised order for stepper motor pinouts, so it's quite common to have to swap the wires over, as is the case here. If your clock hands are jittery or don't move correctly, check whether you've got the wires in the correct order. And the hands themselves I designed in OpenSCAD and 3D printed, and they simply push fit onto the shaft of the motor. So the outer shaft has a diameter of 8mm for the hour hand, and the inner shaft has a diameter of 5mm for the minute hand. And this RS485 module is used to connect the clock to our DMX control network. So I've got an XLR connector here, which I've connected on this side of the module. Now I know the DMX standard specifies that you should use a 5-pin XLR connector, but only 3 of those lines are ever used. And those are pin 1, which is the common, pin 2, which is the inverted signal, and pin 3, which is the positive signal. You might also see those labelled as A and B rather than positive and negative. Now, if your clock doesn't seem to be processing DMX data correctly, you can try swapping those 2 signal lines over. You won't damage anything by having them plugged in the wrong way round, it just might not work. And then on this side, this connector is what goes to our stepper motor shield. And you'll see we've got a ground, VCC, transmit and receive. Although our clock is only acting as a DMX fixture, it only receives DMX data. It doesn't send any out to the network. So you don't actually need to have the transmit pin connected there. You only need a ground, 5 volt, and the receive line connected to the serial GPIO on the shield here. Now let me talk about the structure of that DMX data. And one of the great things about making your own controllers is that you can get them to behave exactly as you want. So you can modify this structure if you want, but the features I decided to go with used 6 DMX channels. And let me talk you through what they do. Channel 1 is a mode selector. And there are 3 modes: run, linked, and independent. In run mode, the hands rotate automatically, and they rotate at the speed that's set in channel 6. So you can use this to indicate the passage of time slowing down, stopping, or speeding up. Now, in independent mode, the hour and the minute hand can be moved independently, and they can be done in 2 ways. You can set the angle of rotation using channels 4 and 5, or you can set them to a specific hour and minute value using channels 2 and 3. Now, of course, on an actual clock face, the hands don't move independently from each other, and the time shown at the moment is actually impossible, because when the minute hand is at half past, the hour hand should be halfway between 1 hour and the one it advances next to. So if you want to make the clock behave normally, that's when you can set channel 1 to linked mode. And what that will do is when the minute hand is moved, you see that the hour hand also advances by the relevant fraction towards the next hour, so that when we go all the way to being on the hour hand is pointing at an hour. Now, one thing to note is that I didn't put in any auto calibration. That would require additional hardware that I wanted to avoid, but there is a straightforward manual calibration routine you can follow to make sure that the hand positions are accurate. So let me just mess this up first of all. Let's say that actually when you installed your hands, you'd put them something like that instead. So what you need to do to calibrate them now is to first of all set to independent mode, and then you want to set the time to a known time. Now you can make this any time you want, but the easiest is to set it to 12 noon, because that's when both hands should be pointing directly up. And having done that, we can now adjust the angles in channels 4 and 5 until that's actually the case. So if I just move the minute hand round a bit further, let's get a look. That looks pretty vertical to me. And then the hour hand, we need to move around to about there. And then having done that, we can now leave these 2 angle channels alone. They're calibrated with the fixed offsetter required, so that this hour and minute value here is the correct on the clock. And now what we can do is we control the clock entirely just using channels 2 and 3. So let's say we want it to be quarter to 7, or if we want it to be a quarter past, I don't know, 3, let's say, and you'll see that the clock hands now stay correct and they stay in sync with each other. We can make it 1 o'clock all the way through to 12 o'clock. But you can of course change this functionality completely if you want by modifying the code that's running on the Arduino. So let's take a look at that. Now, I'm not going to talk through every single line of code because this is quite a long sketch, and as I'm sure most viewers of these videos are aware, there are tools available that can explain Arduino code to you and could even write this for you if you wanted to. But I'm just going to pick out a few of the design decisions I made. So I'm using the Axel Stepper library, which you can download from here. This is a really nice control library for stepper motors that allows you to do things like specify a target position or a relative amount of movement, speed and acceleration, and then you just call an update function and it will provide the appropriate pattern of pulses to make the motors move there. I'm not including a DMX library this time. In some previous projects I've used a library called DMX Simple by Paul Stoffregen. I'm not using that because that's primarily if you want to use an Arduino as a DMX controller, as a master that controls other DMX fixtures. This time, obviously, we are acting as a DMX node. We just receive DMX data. And I've actually manually handwritten the code to receive the DMX frames and process them. So I've not included any libraries for that. Now, in the definitions at the top here, these all relate to the stepper motors. And as is quite common with NEMA 17 stepper motors, these stepper motors have 200 steps per revolution. So what that means is that every time you send a command to make the stepper motor increment a step, it turns by 1.8 degrees. It does that 200 times and then it completes a complete revolution. And that is true for both shafts, the inner and the outer shaft. Now, the problem with that is that when you want to try to revolve like a clock face, like the hours on a clock face, you've either got to subdivide that into 12 for hours or 60 for minutes. And 200 doesn't divide nicely by either of those two values. So you're never going to quite be able to get the hands to line up exactly on certain hour or minute values when there are 200 steps. It won't be a whole number of steps to line up at those angles. Now, we can make that slightly better by using what are called microsteps instead. So a micro step allows the motor driver to kind of hold the motor between steps rather than doing a full pulse of on-off for the coils. It kind of holds the coils at a voltage midway between on and off, and that sort of holds the motor in an in-between step. And you can do micro stepping at various resolutions of whole steps. So I'm using 8 micro steps per whole step here, and that's going to increase the total number of steps required to do one revolution by a factor of 8, which is what we calculate here. Now, you also need to make an adjustment on the shield itself. There's some jumpers which you need to place across just to indicate how many levels of microstepping you're using. You don't have to use microstepping. You can just use 200 if you want, if you don't care to show an exact hour value. And you can increase this to 16 or sometimes 32 microstepping depending on the driver chips you're using as well. But that's what I mean here. So I'm subdividing each of the 200 normal steps into 8, and that's going to allow me to make a pretty precise movement to any of the angular values I want to. These are the number of steps per hour and per minute that we get by dividing those total number of microsteps by 12 or 60. These are the pins which I'm using to control the stepper motors, and that's the standard ramps pinout. Again, if you're using a different sort of a driver shield, or maybe you're using one of the Gerbil controller shields on an Arduino Uno rather than a Mega, these will be different. Simply a step and a direction. I'm also using an enable pin. So some stepper motor drivers always have the drivers enabled. And to hold a stepper motor at a particular value, it normally draws some quiescent current. Even when the motor isn't moving, unlike a DC motor, a stepper motor will always draw some current. And we don't always want that. Once you've moved to the time you want to display, you might want to turn the motor off. So by using the enable pins here, I can actually do that. I can disable the motor when it gets to its target location, and that will stop it drawing any current. I'll show you how I use that in the code a bit later on. Now the DMX values, like I said, I'm kind of handling these manually. So I'm just going to use DMX channel 1. If you're placing this in a network with other devices, you might want to assign that to a different value. And then I'm assigning 6 addresses starting from that value here. So this is going to be the end address. This is just calculating the baud rate at which I'm sending the data. So DMX data is sent at 250 kilobits per second. So that's that value there. And then I'm just going to optionally send some debug data just to check what DMX values are received. Here we've got some configuration for the steppers. This value here makes use of that enable pin I just described, so disable the motors when they're disabled after 5 seconds have elapsed. So if the motor's not been told to move in 5 seconds, it's going to disable it, and that will just save power. It will stop it getting excessively hot and things like that. If you find that your motors are wired the incorrect way around, here is a value you can use to switch them. You can also just swap over the wiring. And these are the values that we're going to use for the Excel stepper library to control how fast the motors move. I'm using 2 steppers. and these are the enable pins. If you wanted to have an hour, minute, and second hand, you'd need to find a triple shaft motor, but you could increase that value there to 3. Here are the clock modes I described and the functionality that they use. And then I've just got a load of global values, which are just going to record where the motor is at the moment, where they're being told to. I've got some DMX debug settings as well. This is actually the ISR routine, which I'm using to deal with the DMX data when it's received. I'm not going to go into this in detail. If you don't understand ISRs, that's fine. This is basically boilerplate code. You can find lots of templates of this online. Or, like I said, there are tools available, let's say, that will write a function like this for you. But it's actually not that hard. It simply populates the DMX values array with values that are received over the serial input from our RS485 transceiver. We set that up here. We've got a couple of helper functions here. We want to work out whether to turn the motors. Let's say we're at 3 o'clock and we want to go to 5 o'clock. Well, that by default will advance the motors clockwise. If you want to go to 3 o'clock and go to 1 o'clock instead, well, a clock would obviously go almost 270 degrees around the clock face to get there, because clocks only move clockwise. That's why we call it that. But for this example, you might want to take the shortest route to get to the new value instead. So that's what we do here. We work out whether the delta, whether the difference in time between where we are at the moment and where we're going to is more than half the clock face in steps. And if it is, we're going to go backwards to that value. Otherwise, we'll move forwards to it. Again, these are all kind of behaviors that you can change if you want to. We've got ways to convert from DMX values, which are between 0 and 255, to a angular degree, which is obviously 0 to 360. Here we've got some debug data and things like that. I've assigned 3 different modes depending on the value set in DMX channel 1. So if it's between 1 and 85, we'll use independent mode. Between 85 and 170 is linked mode, otherwise it's in run mode, and those are the different examples I showed in the video earlier. Some more helper functions here. So these are all just ways of converting between the different kind of units of measurement we have. So we have hours and minutes, which are going up to 12 and up to 60. We have degrees that are going up to 360, and we have DMX channel values which are going up to 255, and these are all just different conversions between them, basically. We've got some more debug information here as well. So if you set that define at the top of the code up here, the DMX debug is 1, what you'll do is you'll have a lot of information printed out to the serial monitor that will just help you figure out what's going on and making sure that your hands are moving where you expected them to, because nobody wants their hands out of control and going somewhere that they weren't expecting. Then a bit further down, so we're into the processing DMX data when it's received here. We update the clock if we're in run mode. And here's the setup function that we run when the code first fires up. So we start a serial connection. That's used for debugging, but I also actually kept in a little ability to manually control the clocks over the serial monitor if you want. So if you wanted to test your clock mechanics in an environment where you didn't have a DMX controller available, you can instead use the serial monitor, connect the IDE like this and load up the serial monitor at the bottom, or any other serial device. And if you send a lowercase h, it will move the hour stepper hand forwards, and uppercase h will move it backwards. Same with the minute hand, forwards and backwards. So that's just a little sort of helper function that you can use to move the clock via serial command rather than DMX if you don't want to do that. So on every iteration of the loop, we process any received DMX data, we update the clock to where it's meant to be if it's running, and that just works out the target values, the target angle, and the number of steps that each stepper needs to move this frame, and then we loop over all the steppers and actually call the run function to make them move that specified number of things. So we kind of do it in 2 steps. We work out the pulses necessary, and then we actually apply them in that step there. Yeah. So that brings me to the end of this DMX controlled clock project. I love clocks and I've used them lots of different ways. Every time I think I've exhausted all the possible things you can do with one, I think of an idea which I've forgotten, or somebody asked me to add a feature, and maybe you've got an idea for a novel way to use clocks which I haven't covered before, in which case please do let me know and maybe I'll do more clock projects in the future. Hopefully I've given you enough information to be able to go away and implement this yourself, or to modify and adapt it to use on the stage or in an escape room or in some other installation. If you want to download the Arduino code I used, along with the wiring diagram, the QLC plus workspace, the 3D models, the hands and all of those things, I'll put them available for download on my Patreon page, where you can also download all the resources to go with any of the other projects in this channel. And I just want to take a very brief moment to say thank you all to my Patreon supporters. I love making these projects every month and sharing them with you, and I'm only able to do that with the generosity of your ongoing support. So I really do appreciate that. Thank you all so much. Otherwise, if you want to leave a comment about this project, you can do that underneath the video here, or you can join the Discord server where people are sharing playful technology projects that they're making all over the world, and you can discuss their ideas and get feedback on them there as well. I'll put a link to that in the description as well. Otherwise, I just want to say thank you all very much for watching, and I look forward to seeing you next time. Cheers, bye.